Hello everyone. Welcome to Enqueue. This channel is about the systems beneath finance, not trading strategies or predictions. I'll sometimes simplify things to focus on intuition. And if you can catch a mistake or a missing nuance, feel free to point it out in the comments. Alright, let's get started. Okay, so let's start by answering a basic question. Why queues matter? When people think about trading systems, they usually think about math, models or signals. But in practice, most trading systems spend far more time moving data between components. As you can see in this short animation, there are different components like market, where the data comes in, and there is strategy component, where the data from the market component comes and it's processed further to generate the signals, and then it's passed on for the execution. So each handoff between these stages adds latency and jitter, and those handoffs are mostly implemented with queues. That's why queue design ends up mattering far more than people expect. Okay, now that we know why queues matter, let's start discussing about SPSC. SPSC stands for Single Producer, Single Consumer Queue. It means exactly one thread processes the data and exactly one thread consumes it. No fan in, no fan out, just a direct handoff between those two threads. Most SPSC queues are implemented as ring buffers, a fixed size array where producer advances a tail index and consumer advances a head index. Conceptually simple, and that's the simplicity. Okay, now that we know why queues matter and what is SPSC, let's talk about the underlying implementation of SPSC, and it's done by ring buffers. So ring buffers are basically a circular data structure, but physically they are just linear arrays in memory. The buffer itself is contiguous, which means predictable memory access and good cache behavior. So as you can see on this short animation at the right, so we have logical implementation of ring buffer, where basically the producers adds on the data and it's mapped directly to the physical memory. And it's basically a circular, so we use a modulo operator to go back on a circular loop. From the CPU's perspective, this still looks like sequential access to memory, which modern hardware handles very efficiently. So why do people go out of their way to design systems around SPSC queues? And why is it so appealing? The short answer is that SPSC queues align extremely well with both hardware and system architecture. First of all, ownership is static. The producer owns the tail index and the consumer owns the head index. There is no competition over who gets to update what. The queue can make progress using simple loads and stores. Secondly, the underlying data structure is fixed size ring buffer, as we discussed already, which is physical contiguous in memory. That gives you good cache locality and predictable memory access pattern, which modern CPUs handle very efficiently. The key point is that SPSC queues are appealing not because they are clever, but because they remove unnecessary sources of unpredictability from the system. Okay, so let's discuss about the use cases of SPSC. Trading systems naturally form single producer, single consumer relationships. A network thread hands packets to a parser. A strategy thread hands order to an execution engine. A strategy thread hands events to a logging or whatever post trade analytics. In each case, there is a clear owner on each side of the handoff. SPSC queues fits this structure perfectly and provide predictable latency. Okay, now we have talked about all the pros of SPSC. Let's talk about some cons. It's very tempting to think that because there is only one producer and one consumer, an SPSC queue is automatically thread safe. That assumption is wrong. It's because of CPUs and compilers reordering. Compilers and CPUs are allowed to reorder operations, and writes made by one core are not guaranteed to be visible immediately to other. Without explicit synchronization, there are no guarantee of ordering and visibility. SPSC removes contention, but it does not remove the memory model. Let's discuss about the CPU reordering. As you can see on the right side, we have a core where we have two variables, data and ready, where basically we are trying to write the data and signal that it's ready for consumption. But due to the optimization done by CPU and compilers, the ready can be updated first and then the data is written on later on. So in that case, the consumer can still see the stale data. Alright, now that we have clear idea of what SPSC queue is, let's start actually understanding how it works. So we have a producer thread which writes to tail position, whereas a consumer thread which reads from head position. Here we have demonstrated a short animation which shows how the logical circular view is mapped to the physical memory layout, and will actually show how the producer thread enqueues while the consumer thread dequeues and reads the value. Let's start from the beginning. So now we have an empty queue where the tail is pointing at the index 0, and similarly it's mapped to the physical memory layout at the index 0. Now it enqueues the value 10 at the index 0 and it proceeds further to the index 1. Similarly the value 20 and it proceeds to the index 2. Similarly it enqueues the value at index 2 and it proceeds further. Now we can see that the head is still at the index 0 and it's ready to consume. So now you can see that the consumer thread consumes the value at index 0, which is the index where head is pointing, and it reads the value 10. And now the head proceeds on to the index 1. Similarly it goes on until the producer stops enqueuing the values and head is done dequeuing all the values. Now that we have clear understanding of how the SPSC queue maps to logical memory, let's dig deeper. So here we have a short animation explaining how the C++ implementation reference works and how the enqueuing and dequeuing works. So let's begin by enqueuing one of the value. So as you can see, always before enqueuing, we ensure that the next tail is not equal to the head, because the logic is that if the next tail equals to head, we imply that the queue is full and we don't want to insert in that case. It's because we always keep one slot empty just to ensure that the queue isn't full. It will be more obvious as we see further. So we'll enqueue one more value, and even in this case, as the head is still at the index 0, it will successfully enqueue. Let's proceed further, and now there is a key part. So the tail is at the index 3, and once we try to enqueue this value, the next tail will point to index 0, but the head is already present at this, and this violates the principle that we have to keep the slot free, one slot free, as the queue is already full. It won't allow to insert any value. But now once we start to dequeue, we'll make sure that the head is not equal to tail. If the head equals to tail, that implies the queue is empty. But now successfully, as the head has read one of the value, we can successfully insert one more value. And let's dequeue all the values. Once it has dequeued all the values, we are at the head equals to tail. As we can see, there is no data here to consume, and if you try to dequeue it, it will say that there is nothing to read. So this is what we're going to implement. Alright, now that we have clear understanding of how SPSC queues work, let's start building it and make our hands dirty. First of all, I've imported all the necessary standard C++ headers and then defined the namespace. Just to keep the data type generic, I've used template type empty, so as we don't want to stick around with a specific data type, and then defined SPSC queue class where we'll define the private member variables. So first of all, as we know, the buffer ring is logically a vector, so we define a vector and named it as buffer, and then capacity, head, tail, and then we'll define the SPSC queue with the parameter capacity, and then we'll use the member initializer list. In C++, class members are constructed before the constructor body runs, and the initializer list lets us construct them directly with the correct values. This avoids unnecessary default construction and reassignment. Now that we also looked on how the enqueue and dequeue functions work, let's start defining it. So the enqueue function will have an item as the parameter, and then we'll define the next tail, which is basically the tail plus 1 modulo capacity, and we'll make sure that the head isn't equal to the next tail, in which case we imply that the queue is full and will return false. If that's not the case, we'll insert the item at the tail index and then update the tail to the next tail and return true. Now let's define the dequeue function. In the dequeue function, first of all, we'll make sure that the head is not equal to tail. If that's the case, then basically the queue is empty, there is nothing to read, and then we'll return the null optional value. If there is data, then we'll dequeue it and read it from the head index, and then update the head, which is basically head plus 1 modulo capacity, and return the item. Also, we'll have the empty function, which basically returns if head equals to tail. Alright, now let's start defining the main function. where basically first of all we have defined the queue size, which is 10, number of iterations, which is 5 million, and then we constructed a SPSC queue and passed on the queue size. We also define a done flag to imply that the producer thread has done inserting all the values. Alright, now we have to construct two different threads, producer and the consumer. Producer will insert at the tail index while consumer will read from the head index. So we'll basically insert up to 5 million values, and we will use the Enqueue function to insert the values, and once the producer is done inserting, it will flag the done flag as true. Similarly, we will be defining the consumer thread, where basically it will check if the done flag is true. Then in that case we don't have anything to read, and if that's not the case, we'll keep on reading, and also we'll make sure that the queue isn't empty. So if either of the case is true, then we'll keep on reading, and it will dequeue the values, and we defined a consumed vector where basically we'll insert all the dequeued values, and then we start both of the threads using the join operator. After the producer and consumer threads are done reading and writing, we'll check the results. So basically I'll check all the duplicate values and the lost values. It will be more obvious once we actually execute the code. So for that, let's start executing the code. And now it's compiled, and I'll run. So as you can see, the consumed values are 5 million, there is no lost value, there is no duplicate value. We'll execute it again, and you can see there is one lost value and one duplicate value, and this is the lost value, this is the duplicate value. We keep on running for a few more iterations. So you can see the number of lost values and duplicate values keeps on changing. Why is that happening? Come on, let's discuss. We saw that we were getting garbage data and were losing the updates. So let's start. Let's start by looking at the execution of the producer, consumer, enqueuing, dequeuing, and how the CPU reordering works. On the left we have the producer core in green, and on the right we have the consumer core in the blue, and we have the shared RAM. Notice on our initial state the queue is empty because head equals 10, but crucially look at the buffer's 0th index. It holds the value 10. That's the stale data from the previous run, or garbage we shouldn't be reading again. Let's kick off the producer. It wants to enqueue the value 99. Look at the code on the left. The buffer tail is 99, the CPU executes this, but here is the catch. It doesn't hit the RAM instantly. It sits in the producer store buffer, that blue box, waiting for cache coherency. Next line, tail equals to next. The producer needs to update the tail index to signal that data is ready. Look at the pipeline visual. The tail update is queued up behind the data write. In a simple world, they would execute in the order. But CPUs aren't simple. They do some CPU reordering for optimization. The CPU notices that the address of tail and the buffer are completely independent. To optimize performance, it decides to reorder them. If you see that, that's the bug. The tail update jumped into the fast lane, completely bypassing the stale data write. This is the moment of failure. Look at the shared RAM. The global tail is now 1. To the rest of the system, this signals new data is ready. But look at the buffer 0. The data is still the old 10. The signal arrived before the payload. The memory state is inconsistent. Now the consumer core. On the right to EXA, it checks, is head equal to tail? No, tail is 1, head is 0. The consumer thinks, great, data is ready. It executes the read. But because the producer's 99, it's still stuck in private buffer on the other core. The consumer read what is actually in RAM. It reads 10. We have just processed a duplicate value. The consumer has no idea, it just read garbage. The consumer finishes its job and advances the head index, thinking it succeeded. Finally, milliseconds later, the producer's store buffer flushes. The value 99 overwrites the slot in RAM, but it's too late. The head pointer has already moved past the slot. That 99 will never be read. This is the lost data. So as you can see, simply relying on int variables isn't enough. The hardware doesn't guarantee the order you see in your source code. It all happens in memory. How do we fix this? Well, there are two ways. In the next video, we are going to take the heavy hammer approach and fixing this using Mutexes and logs to force a synchronization. And then in the later video, we'll finally achieve true synchronization using the automix to prevent reordering without using log, creating a true log-free queue. In this video, we'll try to fix it using Mutexes. Not because they are fast or performative,
but because it sets a correctness baseline. So let's dive in. Before that, we need to understand what mutex are. A mutex is a synchronization primitive that enforces mutual exclusion. You can imagine it as a lock that guarantees that only one thread at a time can execute a protected section of the code. In essence, no other thread can access the same portion. So it has the exclusivity and lock over that critical section area. Alright, now that we have understanding of mutex, let's dive in and fix the naive SPSC queue. We start with two threads, a producer and a consumer. The producer wants to enter the critical section, it calls lock. Now look at the central panel. This isn't a simple variable assignment. The hardware prepares an atomic compare and swap. Under the hood, mutexes use compare and swap operation at really low level. So it expects 0 and the actual value is 0. So it's good to go for acquiring the lock and swaps it with 1. So now the mutex state is 1. It's locked. Now the consumer calls lock, but what happens? It does the CIS comparison again and it expects 0, but it actually got 1. It means that the mutex is already locked, so the consumer can't acquire the lock. So it fails. Now in a bad implementation, the consumer would spin in a loop, burning 100% of your CPU. But mutex is smarter. Since the lock is taken, the C++ runtime makes a syscall. It tells the OS, put me to sleep until this address changes. The consumer is not blocked, saving your battery life. Eventually the producer finishes the execution and it calls mutex unlock. This does two things. First, it sets the atomic flag back to 0. Now the mutex state is 0. It's unlocked. It signals the OS scheduler to wake up any threads sleeping on this address. This wakes up the consumer. It retries that cache operation, finds that the value is 0 it was looking for, swaps it 1, and finally enters the critical section. This is the happy life cycle of a lock. But there is a massive problem. Look closely at the producer. We manually called lock, unlock. What happens if we return early? What if code throws some exception? We skip the unlock. The consumer stays blocked forever. This is how you get deadlock. This is why in modern C++, we almost never call lock and unlock manually. We use RAI, that is resource acquisition is initialization. We wrap the mutex in a std lock guard. It generates a constructor that locks mutex immediately and destructs it when its scope ends. So you don't have to manually lock and unlock, it does it automatically for you. It makes your code cleaner, safer, and deadlock resistant. So remember, under the hood, it's atomic hardware instructions. Now let's dive into the code. In the last video, we saw the exact implementation of naive SPSC queue. In this video, we'll be fixing it using a queue to establish correctness. We add mutex to the queue and guard all the shared data, the head, the tail. Every enqueue and dequeue operation acquires the lock before touching shared data. So here we have defined the mutex and we'll be using lock guard as discussed already, that it's constructed and destructs automatically when it goes out of scope. This makes the code exception safe and prevents common locking mistakes. In enqueuing, we acquire the lock, check whether the queue is full, write the data, and advance the tail. While the lock is held, the consumer cannot observe any intermediate state. Similarly, in the dequeue, we acquire the lock again. Before checking if the queue is empty, read the data and advance the head. Because both sides uses the same mutex, there are no data races. This implementation of mutex gives us two guarantees. Mutual exclusion happens before relationship. When the producer releases the lock, all of the data it writes become visible to the consumer when it acquires the lock. That's the key difference from the naive version. Now let's start executing and see the result. I've already compiled it and you can see that there are 0 lost values and 0 duplicate values, and we have achieved the correctness we were looking for. Just to make sure it didn't happen by chance, we'll execute it again. You have noticed that it takes longer to execute the mutex code. It's because acquiring lock and releasing the locks takes time, and also it adds extra synchronization overhead, so it's a bit slower than the naive implementation. On the other hand, if I execute the naive implementation of the code, you can see it's faster, and we also see that there are data races and duplicate values, lost values. So finally we have achieved what we were looking for, the correctness. Though it's not that performative, it's a bit slow, but the correctness is all that matters, and we have achieved this. In the next video, we'll make this code performative and faster using the automix. Let's recap our journey so far. We started with the naive implementation. It was incredibly fast but completely broken because of race conditions and memory reordering. In the last video, we fixed it using a mutex. It was safe, but it was super slow because thread had to sleep and wake up. In today's video, we're going to reach the final goal using automix. We are going to build a queue that is both safe as well as fast. We do this by manually controlling memory barrier. Let's begin. We start in the producer thread. Just before we need to know where to write, we load the tilde index. In the mutex version, we would have locked the mutex. Here, in this version, we just load the atomic variable using a memory order relaxed. Why relaxed? Because only the producer writes to the tail. We don't need synchronization just to read our own nodes. It just adds overhead. So we are proceeding with memory order relaxed. Now we check for space. We compare our next slot against head. This is our first barrier. In the naive video, this is where we risk reading a stale value and overwriting unread data. The acquire shield guarantees that if the consumer has updated head, we definitely sees it. It syncs up with the consumer's timeline. Now we have space. We write data to the buffer. Pay close attention to this visual. See how the data is ghosted and dashed. This is exactly what broke our naive implementation. Right now the data is sitting in the producer CPU cache, that is the store buffer. It hasn't necessarily flushed to RAM. If we updated the tail index right now, the consumer might wake up, see the next index, but read garbage data because this A hasn't yet arrived yet. So how do we fix it? Here is the fix. We use the release barrier. We are about to update tail to publish the record. We use store release. Unlike the mutex which stops the world, release acts like a barrier. It forces all pending data to flush into the main memory before the tail variable is allowed to change. It enforces the order: data first, index second. Now the tail updates to 1. Because of that release flush, we have a contract. The data now is visible at the index 1. You cannot see the index without also being able to see the data. Now let's jump to the consumer. It wakes up and checks its own head index. Again relaxed, ordering is fine here, it's local data. Now the consumer checks tail to see if there is work to do. In the mutex version, we would acquire a lock here. But in this version, we use an acquire barrier on tail. This shield works with the producer's release. It invalidates the consumer's local cache. It says if you see the tail has moved to 1, you are also required to accept all the data flushes that happened before that move. This makes sense, right? This ensures we never read the ghost version of the data. We never read the stale data. So because of that acquire release handshake, the data is solid and up to date. We copy it out safely. Finally, we update head using release to tell the producer the slot is free. This is the standard pattern for lock-free programming. Data is the payload, the atomic variable is the signal, and the barriers ensure they arrive in right order. I want you to burn this image into your mind. This is lock-free pattern. We have a payload here. This is your buffer data. It is physically just bytes in RAM, but to the rest of the world, it's an invisible data. The signal on the right, this is your atomic variable, head or tail. It acts like a flag. The barriers, these are the acquire and release commands. They are the glue. If you change the signal without the barrier, the payload arrives late and your code crashes. But if you use the barrier, you guarantee that whenever the signal is raised, the payload is already waiting. Okay, now let's dive into the code. Let's see how the atomics work and how we achieve a performative and safe SPSC queue. So now let's walk through the actual C++ implementation. Structurally, nothing has changed. We still have a fixed size string buffer, head index, tail index as usual. The only difference is how synchronization is done. Instead of the mutex, we now have atomic. This works because of a key constraint. Only the producer ever writes tail and only the consumer ever writes head. That single write property lets us avoid more expensive synchronization. So let's start with the Enqueue operation. We load the current tail using the memory order relax. This is safe because, as I already explained, only the producer writes head. We don't need ordering here, just the value. Now we do the full check. We check whether the queue is full. We compare against head. This load uses the memory order acquire. That acquire load guarantees we see the most recent head that is released from the consumer, along with all the memory effects that happened before it. So this is the key part here. And then, as usual, we do the memory write, but what matters is what happens after this. Here we have tail.store and we are using memory order release. This release store is the key. It guarantees that the buffer write happens before the updated tail becomes visible to the consumer. So here we are achieving the synchronization. Without this, the consumer could observe the new tail value and read stale or uninitialized data. That's exactly the failure mode we saw earlier in the naive version. So we are fixing it using the acquire release synchronization pair. I hope that makes sense. Now similarly, moving to the Dequeue operation, we do the same load using the memory order relax, as consumer is the only one updating the head. And then we do the empty check, and here we do the memory order acquire. This pairs with the producer's memory order release and guarantees we see the updated tail. We also see the buffer write that happened before it. So as soon as the memory order release kicks in, the memory order acquire sees the updated buffer data as well as the updated tail. And similarly, then we do the head store using the memory order release, and it makes sure that the producer sees the updated head value. And similarly, we do the empty check using the relaxed and the memory order require. Here notice that we use head as memory order relaxed because we do the empty check only in the consumer. So for the consumer, the head is only updated by itself, so we don't need like a overhead synchronization of doing released or acquire. So we have used relaxed, and similarly the tail, we do the acquire on it. And then the standard, we run the thread producer consumer as we have already seen. Okay, now let's execute the code. I've already compiled it. I'll execute it. So you can see there are no lost values, no duplicate values, no hangs. We'll execute it again to make sure it works perfect. Yeah, you can see again there is no lost value, no duplicate. So we have achieved the synchronization which we were looking for. But you might have noticed, unlike the Mutex version, there is no blocking or no context switching. So this version is faster and non-blocking, but it comes at the cost. The code is harder to reason about, easier to get subtly wrong, very sensitive to memory ordering mistakes. This is why lock-free code should always be built on top of known correct baseline, as we have done. We have created the correct baseline using the Mutexes, and then on top of it, we create a lock-free version of it using the atomics. That's the end of the full SPSC queue journey. We have seen the naive implementation, correctness using the Mutexes, lock-free implementation with atomics, same queue, same logic, different synchronization. That's the complete journey. If you followed around through the details, thanks for sticking with this. Please subscribe, share, and like. See you in the next one.